All right, in this video, I'm going to talk about the phasor diagram of an inductor. So we have an inductor on an AC circuit. I'm not interested in the rest of the circuit. So I just look at these two important quantities, the current that passes over the inductor and the potential drop on the inductor. And we would like to find the relationship between these two. Let's remember an important point that we have talked about before. So we cannot really define potential, the concept of potential, electric potential, for an inductor, because basically inside the inductor there's a magnetic field which changes with time, and that produces an induced electric field. And we have seen that this induced electric field is not conservative, so therefore we cannot really define a meaningful potential quantity. So what we should really be talking about in here is the EMF produced by the inductor. But on the other hand, a lot of people just forget about that fine difference, since we are going to talk about not the inside of the inductor but the terminals of the inductor. They still call the the relevant quantity in here as not as the EMF but the potential drop. So it appears that no harm is done when we do that. But just keep in mind that, of course, in some certain situations, of course, that's a very important difference. So that's something that we should keep in mind. But apart from that, I'm also going to use their sloppy language and call this as the potential drop. Again, in here, the arrow is important. This is the direction along which we measure the current. It's also the direction where I also define the potential drop. So in this case, this is equal to a VA minus VB again. So this is VAB. So how do I relate this to the current? So let's just remember this. So for an inductor like that, where there's a choice of direction like this, and the current is along that direction. So what we did was we replaced this with an EMF device like that, and the EMF of the EMF device was equal to, given by the Faraday's law. So therefore there's a minus sign in here, is in Faraday's law, and then we have L times the rate of change of the current. And the reason is that, of course, the flux through the inductor is equal to L times I. In any case, so that was point A and that's point B. So therefore, in this case, this potential difference VAB would be minus the EMF. So therefore, this is plus L di over dt. Okay. So as a result, for an inductor, the potential drop is equal to L times di over dt when the current is I. So that means I'm going to write it in here. If the current is like that, it is I0 times cosine omega t. I choose the phase angle for the current to be equal to 0. In that case, potential drop on the inductor would be L times the derivative of this thing is equal to minus omega times I0 and sine omega t. All right, there's a minus sign that appears in here. This may cause a headache. So this minus omega L times I0 sine omega t. I'm just going to do it like this. I think I'm going to first carry this minus sign to the argument of the sine function. Right? So therefore, I'm going to write this thing down as omega L I0 times sine of minus omega t. And next, I'm going to use this relationship. The sine of any angle is cosine of 90 degrees minus the angle. So here the angle is minus omega t, so I'm going to write it down like that. So you can see that the potential drop on the inductor would then be omega L times I0, and then the cosine of omega t plus pi over 2. So therefore, if the current is given by that expression and the potential drop is given by that expression. So we can read the amplitude in here. Amplitude as a positive number is also positive in here, so that's one of the things that we should notice. And we can also read the phase difference in here. So you can see what is what in here. So we can then draw the phasor diagram quickly. Right, so if the current is like that, the current vector on the phasor diagram is like that, its amplitude is I0, and this angle is equal to omega t. The potential drop on the inductor is VL, is like that, therefore, where the angle is omega t plus 90 degrees. So therefore, this vector has a magnitude, a direction like that. So the angle between them, between the potential drop and the current is 90 degrees. So I call the amplitude VL0. So I'm also going to write down the amplitude, but let's start with our phase relationship. So we say that VL leads, the potential drop leads current by 90 degree phase difference, or we say that the current lags behind the potential drop by 90 degrees. So the phase information is important, so that's our first relationship. The second one is the relationship between the amplitude of the potential drop and the current. So that's omega L times I0. So we just call this quantity as the inductive reactance. So XL is omega L, so that's called the inductive reactance of the circuit. Again, the unit is ohms. You can check the units by yourself. And there's this third thing, that's the average power. So I'm going to write it in here. So average power. This is just like the case for the capacitor average power. Basically, the inductor is a device that doesn't consume any energy. It doesn't convert energy into a form that is removed from the circuit. No, that's not the case. So it just stores some energy and then gives that energy back to the circuit. So therefore, the average power is equal to 0. But it is nice to see that this is also the result of that angle between the current and the potential difference. So therefore, I can express this as the dot product between the current and the potential drop. So that's equal to 0. All right, so as a result, again, these three important things, let me raise this one star and move it in here. In here, so that's VL0 divided by the current. The ratio of the amplitudes of the current and the potential difference is the reactance. Right. So first important relationship is the phase difference in here. Second one is the reactance, the relationship between the amplitudes. So by using this, once I know the current as a function of time, I can find the potential drop as a function of time. And the third thing is, of course, the fact that the average power on an inductor is equal to 0.